All right, let's dive deep today into the world of AI and biology.
That sounds good.
We've got a really interesting collection of articles and notes you sent over.
Yeah.
It's obvious you're really interested in where this whole field is going. So for this deep dive, we're going to give you a concise 10-minute briefing on the biggest innovations in AI and biology from just the last few months.
Wow.
The big leaps forward, exciting advancements, and the areas that are, well, still being explored.
But I mean, it's amazing to see how fast things are moving in this field. It seems like just a few years ago, the big news was AI predicting static protein structures. And now we're talking about AI generating entire simulations of protein movement and behavior.
It's true, like those protein structure predictions from AlphaFold we all heard about.
Exactly.
But, like your notes point out, knowing the shape of a protein is only one part of the story.
Yeah.
Like having a blueprint tells you the components, but not how the machine actually works, in motion.
Exactly. That's why there's been such a big push to understand protein dynamics, how these molecules move and interact over time.
Hmm.
And that's where AI is really starting to shine.
It's amazing to think about AI modeling those tiny molecular machines in action.
It is.
One of the articles you sent mentioned this new AI called MDGen,
Oh, yeah.
and they were comparing it to Sora, that text-to-video AI, but for molecules.
It's a good comparison. MDGen can essentially create videos of
Mhm.
how proteins move and change, something traditional simulations have really struggled with.
So that's a game changer, right? Being able to actually visualize those movements must be so helpful for researchers.
Absolutely. Gives them a whole new level of insight into how proteins function, how they interact with each other, and how they might be targeted with drugs.
It's like having a molecular microscope that can not only see the structure, but record the action too.
And what's even more impressive is that MDGen can do things that traditional simulations can't, like filling in missing parts of a protein structure
Yeah.
within a dynamic trajectory.
Wait, so it can predict what those missing pieces should look like
Uh-huh.
and how they would move.
Yeah, that's exactly what it's doing. And it has huge implications for things like designing enzymes and understanding complex biological processes.
So it's not just about watching the show, it's about directing it too.
That's a great way to put it. AI is becoming more than just a tool for analysis. It's becoming a partner in design.
And it's not just individual AI models working in isolation, right? Your notes mentioned a shift towards integrated workflows,
Yeah.
which sounds a lot more sophisticated.
You're right. The field is moving beyond using single AI models for very specific tasks. Think of it like an assembly line. Instead of each station being independent, now they're all linked together,
Oh, okay.
each one feeding into the next.
So that's how these AI-driven workflows are taking protein design to a whole new level.
Exactly. You might have one AI model designing the shape of the molecule,
Mm-hmm.
then another filling in the sequence of amino acids, and then another simulating its dynamics, all working together seamlessly.
That's amazing. And these workflows are already being used to design proteins with incredible precision and for purposes we could have only imagined before.
Absolutely. There's been some really interesting work, for example, using AI to design enzymes that can break down harmful bacteria.
Oh, wow.
These enzymes essentially pull apart the bacteria's infection mechanism.
Wow. That's incredible. So it's like designing microscopic dismantling crews to target infections.
That's a great analogy, and that level of precision is only possible because of these AI-driven workflows. They allow researchers to fine-tune every step of the design process, which leads to these remarkable breakthroughs.
It sounds like these workflows are revolutionizing not just how we design proteins, but what we can actually achieve with them. Now, your notes also pointed to peptides
Hmm?
as a new frontier in drug development.
Yes.
These short chains of amino acids are easier to manufacture and deliver than larger proteins, making them ideal for therapeutics.
Right. You're absolutely right. Peptides have always been attractive for drug development, but they've also been notoriously difficult to work with.
Yeah.
You see, their flexibility and lack of stable structure made designing and predicting their behavior really challenging.
So how is AI tackling this peptide puzzle?
Well, new AI models like PepFlow are starting to make real progress in designing peptides and similar structures like components of antibodies. They're able to predict how these molecules will fold and interact, which is crucial for developing effective therapeutics.
That's exciting. It sounds like we're on the cusp of a peptide revolution in medicine, and AI is leading the charge.
I think that's a fair assessment. AI is definitely unlocking the potential of these smaller molecules, paving the way for a whole new generation of treatments.
And you mentioned another model in your notes that really caught my eye, ESM3. It seems to be doing something truly remarkable.
ESM3 is definitely pushing the boundaries of what's possible with AI and protein design. What's so unique about it is its multimodality. It can understand not just the sequence of a protein, but also its 3D structure and its function, all at the same time.
That's incredible. It's like having an AI that can read the blueprint, see the finished building, and understand what it's used for, all at the same time.
That's a great analogy. And this ability to integrate different types of data is a huge leap forward. It means that ESM3 can be used to design proteins with completely new functions, things that haven't been seen in nature before.
Wow. That opens up so many possibilities. Are there any examples of ESM3 actually creating something totally new?
Yes, there are. The developers of ESM3 were able to use it to design a protein that fluoresces, something it wasn't specifically trained to do.
So it's not just mimicking what it's seen before, it's actually creating something new.
Precisely.
Yeah.
And that's a really powerful demonstration of the potential of this technology.
It sounds like we're moving beyond simply understanding proteins to actually engineering them at a much deeper level.
I think you're right. AI is giving us the tools to design and create proteins with unprecedented precision and control.
It's remarkable to think how far we've come in such a short time. It makes me wonder what the next few months will bring.
Oh, it's an exciting time to be working in this field, that's for sure.
I bet. And speaking of exciting developments, one of the things that kept popping up in your notes was the concept of AI agents.
Yeah.
It sounds kind of science fiction-y, but it seems like they're becoming a real force in protein design.
It might sound futuristic, but AI agents are already playing a significant role in protein design. Think of it as an AI system that acts like a project manager,
Right.
overseeing and guiding that whole design process.
So they're not just designing proteins themselves.
Right.
They're like managing the whole project.
That's right. These AI agents can set goals, make decisions, adapt to new information, even generate hypotheses, all with minimal human intervention.
That's incredible. So it's like having a tireless, super efficient research assistant who never sleeps.
That's a great analogy. These agents are already automating a lot of tasks in the protein design workflow. For example, they can optimize the parameters of other AI models, making sure they're performing at their best. They can also select the most appropriate AI model for a given task. Kind of like picking the right tool for the job.
So they're like the master craftsman, choosing the perfect tools and fine-tuning them for each project.
Exactly. And that's not all. These AI agents can also evaluate the results of other AI models, sifting through the data to identify the most promising designs. They can even generate new hypotheses, suggesting novel avenues for exploration based on the patterns they've learned.
It's almost like they're thinking for themselves.
It's getting close to that. As these AI agents continue to evolve, they're likely to play an even bigger role in orchestrating the whole protein design process. From identifying targets to designing and testing proteins, these agents could really streamline and accelerate every stage.
It's like having a whole team of AI experts working tirelessly behind the scenes.
And the shift towards AI-driven workflows isn't just about speed and efficiency. It's also about pushing the boundaries of what's possible. You see, these AI agents can explore a vast design space that would be impossible for humans to search through manually.
So they might be able to discover like entirely new types of proteins with functions we've never seen before.
That's exactly the kind of potential we're talking about. It's a truly exciting time to be working in this field.
It sounds like it. Now, you mentioned that these AI agents are often built on large language models, the same technology that powers chatbots like ChatGPT. How do these language models, which are usually trained on text, adapt to the world of protein design?
That's a great question. At their core, large language models are incredibly good at recognizing patterns. They're trained on huge amounts of text data, learning to identify patterns in language and generate new text that follows those patterns.
So it's like teaching a computer to speak and write by giving it like a massive library of books.
Exactly. And this ability to recognize patterns isn't limited to just text. It can be applied to any type of data, including the data that describes proteins.
So they can learn to read the language of proteins.
That's right. By training these language models on protein sequences, structures, and functional information, we can teach them the language of biology.
And once they've learned that language, they can use it to design new proteins.
Exactly. They can generate new protein designs, suggest hypotheses, and guide the overall design process, all by using their understanding of protein language.
That's amazing. So it's like having an AI translator who can speak both human language and the language of proteins fluently.
It's a powerful example of how AI is bridging different domains of knowledge, bringing together language, biology, and computer science.
It sounds like a recipe for some really groundbreaking discoveries.
I think so too.
But with all this potential, are there any risks or concerns about using these AI agents and large language models for protein design?
That's an important question. While AI agents and large language models offer immense potential, it's important to use them responsibly and address potential challenges.
So what are some of the key concerns that researchers are thinking about?
One concern is the potential for bias. If an AI model is trained on biased data, it could unknowingly perpetuate, even amplify, those biases in its outputs.
Right.
This could lead to designs that are inaccurate or unfair.
So it's like teaching a child to speak, but only exposing them to a limited vocabulary. It can limit their ability to communicate effectively.
That's a good analogy. We need to make sure that the data used to train these AI models is diverse, representative, and free from bias.
That makes sense. So data bias is a key concern.
Yes, it is. Another concern is the issue of explainability. AI models, particularly deep learning models, can be very complex, making it difficult to understand how they reach their decisions.
So it's like having a black box that spits out answers, but you don't know how it got there.
Exactly. This lack of explainability can be problematic, especially in fields like medicine, where understanding the rationale behind a decision is crucial.
Like a doctor prescribing a treatment without explaining why, leaving the patient feeling, uncertain, potentially distrustful.
We need to develop methods to make these AI models more transparent and explainable, so scientists can really understand how they're working and verify their results.
So explainability is crucial for building trust in these powerful tools.
Absolutely. And finally, we need to be aware of the potential for AI systems to be misused. As AI becomes more powerful, we need to safeguard against its use for harmful purposes.
So it's like any powerful technology. It can be used for good or for evil.
Exactly. We need to establish ethical guidelines and regulations to ensure that AI is used responsibly in protein design and other fields.
Those are all important points. It seems like navigating the ethical and societal implications of AI will be a crucial part of realizing its full potential.
It absolutely will. And this conversation needs to involve not just scientists, but also policymakers, ethicists, and the public.
It's a shared responsibility to ensure that AI is used for good and that its benefits are shared equitably.
I couldn't agree more.
Now, we've talked about the potential risks, but let's shift back to the positive. What are some of the ways that AI-powered protein design could improve human health and solve global problems?
The possibilities are truly vast. AI is poised to revolutionize medicine, agriculture, energy, material science, and many other fields, all thanks to its ability to design proteins with tailored functions.
That's an impressive list. Could you give us some specific examples of how AI-designed proteins could make a difference in these areas?
Certainly. Let's start with medicine. AI is already being used to develop new drugs, vaccines, and diagnostics, and its impact is only going to grow.
So we can expect to see AI-designed proteins playing an even bigger role in treating diseases.
Absolutely. We could see personalized therapies that are tailored to an individual's unique genetic makeup. We could see new antibiotics to combat drug-resistant bacteria and vaccines that provide long-lasting immunity against emerging infectious diseases. We could even see new treatments for chronic diseases like cancer, Alzheimer's, and diabetes.
It sounds like AI-powered protein design could lead to a new era of precision medicine, with treatments that are more targeted, effective, and personalized.
That's exactly the kind of potential we're talking about. And beyond medicine, AI-designed proteins could revolutionize agriculture. Imagine crops that are more resistant to pests and diseases, require less water and fertilizer, and produce higher yields.
That would be a game changer for global food security.
It would. AI could help us design proteins that enhance plant growth, improve nutrient uptake, and provide protection against environmental stresses, making agriculture more sustainable and efficient.
It's amazing to think that AI could have such profound impact on our food systems.
And that's not all. In the realm of energy, AI-designed proteins could play a key role in developing new biofuels, improving the efficiency of solar cells, and even creating new methods for carbon capture and storage.
So AI could help us transition to a more sustainable energy future, reducing our reliance on fossil fuels.
Exactly. And in materials science, AI-designed proteins could lead to the creation of new materials with unique properties. Imagine self-healing materials, biocompatible implants, and biodegradable plastics.
It's incredible to think that AI could help us create a more sustainable and biocompatible world, where materials are designed with the environment in mind.
That's the kind of future we're striving for. These are just a few examples of the vast potential of AI-powered protein design. As this technology continues to evolve, we can expect to see even more creative and groundbreaking applications emerge.
It's an inspiring vision of the future, a future where AI empowers us to solve some of the world's most pressing challenges.
And it's all thanks to the incredible versatility of proteins.
Now, as we wrap up this exploration of AI and protein design, what are your thoughts on the future of this field? What trends and developments are you most excited about?
Oh, the field is moving so quickly. It's hard to say exactly what's next, but
Yeah.
there are a few key areas that I think really stand out.
Okay, so what's on the horizon for AI and protein design? What's got you particularly excited?
One of the most promising trends is the development of even more sophisticated AI models,
Yeah.
models that can really capture the true complexity of how proteins behave in living systems.
So we're moving beyond just looking at static structures or simple interactions.
Exactly. The new models being developed are taking into account things like dynamic movements of proteins, how they change shape,
Yeah.
how they're affected by modifications, and how they interact with their environment. It's a much more holistic view.
It sounds like a huge leap forward, like going from a flat photograph to like a 3D movie.
That's a great way to put it. And this increased sophistication is going to allow us to design proteins with much greater precision for even more challenging applications.
It's incredible to think about the possibilities that this opens up.
Another trend I'm really excited about is the increasing integration of AI with other scientific disciplines, like physics, chemistry, and biology.
So breaking down the barriers between different fields.
Exactly. Protein design is inherently interdisciplinary, and AI models need to be able to draw on insights from all these different areas to create truly innovative designs.
It's like building bridges between different islands of knowledge. So AI can access a much wider range of information and perspectives.
Precisely, and this integration is already leading to some really interesting collaborations between researchers from different backgrounds. It's a much more holistic and creative approach to protein design.
That's fantastic. And what about those AI agents we were talking about earlier? What role do you see them playing in the future of this field?
AI agents are definitely going to be a major force in protein design. We're already seeing them automate more and more complex tasks, and that trend is only going to accelerate.
So they'll be handling more of the heavy lifting, leaving human researchers free to focus on the bigger picture.
That's right. These AI agents can sift through massive amounts of data, identify patterns, generate hypotheses, and even design experiments, all much faster than humans can.
It's like having an army of tireless research assistants working around the clock.
Exactly. And what's even more exciting is that these AI agents are enabling us to explore a vast design space that would be impossible for humans to search through manually.
So they could potentially uncover entirely new classes of proteins with functions we've never even imagined.
That's the potential we're talking about.
It's mind-blowing to think about the possibilities.
It really is.
And what about the impact of all this on society? How do you see AI-powered protein design shaping the world in the years to come?
I think the potential is truly transformative. AI-powered protein design could revolutionize medicine, agriculture, energy, material science, countless other fields. It could help us develop new treatments for diseases, create more sustainable food systems, transition to cleaner energy sources, and design materials that are more compatible with the environment.
It's an inspiring vision of the future.
And it's not just about solving problems, it's also about creating new possibilities, expanding the boundaries of what's possible with biology. AI is giving us the tools to design proteins that can perform functions that have never been seen in nature, opening up completely new avenues for innovation.
It's like unlocking a secret code that allows us to communicate with and control the very building blocks of life.
Exactly. And this ability to speak the language of proteins is what makes AI so transformative. It's changing the way we understand and interact with the natural world.
It's incredible to think that we're living in an era where this is all possible.
I completely agree. It's an exciting time to be a scientist, and I'm incredibly optimistic about the future we're building. A future where AI empowers us to create a healthier, more sustainable, and more innovative world.
That's a fantastic vision to end on. Thanks for taking us on this deep dive into the world of AI and protein design.
It was my pleasure.
And to you, our listener, keep exploring, keep learning, and keep asking questions. The future of this field is in our hands.
And who knows, maybe you'll be the one to make the next groundbreaking discovery.
Until next time, keep diving deep.